third approximation, and we'll never quite get to a third approximation because we have to deal with temperature and all that. Beta DC, if beta DC is 30, then alpha DC is important because a beta DC of 30 would be 1 over 30, and no, it wouldn't. If a beta DC is 30, then the base current is a pretty high part of the emitter current, and we have to keep it in mind. Let's look at a common emitter circuit. We connect this transistor in such a fashion as we have ES1, or actually it's ES2, ES1, or you can call that E base or E collector. Anyhow, we need current limiting in the collector and we need current limiting in the base, otherwise we'd have runaway. We'd have only a forward bias diode to limit this current. And we need this current also limited. Now keep in mind that the base current controls a larger collector current. In this we have the two loops for current flow. We have the collector loop here, and we have the base loop here. Yeah, and we're back to conventional current flow. They call this a common emitter circuit because of the emitter is set on ground. It's common. That's the common point. If you look at this diode here, it has a forward drop of 0.7 volts. Let's look at it again. If you have a current flow through it this way, you're going to have a 0.7 volt drop from here to here. Let's look at this in a circuit. This circuit is a common emitter circuit. We have 10 volts here, 2 volts here. We have a RC of 1 k ohm, a RB of 100 k ohm. If we have a 2 volt here, our KVL for this is 2 volts minus IBRB, whatever current this is, minus the 0.7 volt drop here across this base emitter junction, and it's all equal to 0. 2 volts minus 0.7 volts is 1.3 volts. And we don't know what IB is, so let's put RB in there because we know that. So 1.3 volts divided by 100 k ohms is 13 microamps. So we have 13 microamps here, and we said that the base current controls the collector current. So if that's the case, then we need to know what beta DC is. In this case, we're given beta DC of 200. So collector current is equal to beta DC times IB. Base current is 13 microamps times 200, which is beta DC, comes out to 2.6 milliamps. Great, that means we have 2.6 milliamps of base current, and the thing that controlled it is this transistor here. What does that mean when we're talking about the voltage drop across this? That means 2.6 milliamps times 1 k ohm. There's 2.6 volt drop across RC. Hmm. Well, how can that be? What is the rest of this? Because it has to be a KVL loop. KVL for the collector loop. Let's see, we started out with 10 volts minus IC RB minus, how about voltage collector to emitter is equal to 0. Let's find out what this is. Voltage collector to emitter. So we have 10 volts minus 2.6 volts is equal to VCE. Okay, so we have 7.4 volts equals VCE. Oh, so the transistor has, if I increase the current on the base, then the transistor will actually reduce VCE because it'll allow more current to flow in that circuit. So if we take this 7.4 volts VCE and plug it in, the voltage drop. The voltage from here, VC, to here, VE. So that would be VC minus VE, because this is 0. It's equal to 7.4 volts. Very interesting circuit. If I increase the current here, the voltage here is going to go down. If I decrease the voltage here, then the voltage here is going to go up. Very interesting device.